This is the last lecture on the diffusion equation. D is a diffusion constant. And remember that we started thinking about this particular problem because we said, imagine that there is a diffusing particle that's moving around like that. The random trajectory is a consequence of the fact that it's surrounded by lots of other small particles which we cannot see. And this leads to some unpredictable trajectory which we can only make statistical statements about. So we can say if I started this off at a particular point at time t equal to 0, the probability of finding it at some distance, say x in one dimension, at some later time t is something that we can calculate. We cannot say it will follow exactly this trajectory. All we can give is a probability distribution. And this is a non-trivial probability distribution because at different times it looks different. So in that sense, it's a function both of the coordinate x and of the time t. And it evolves as a function of time. So we wrote down what this was in one dimension and also in 3 dimensions. In one dimension, this was 4 pi dt to the power 1/2 e to the power minus x squared 4 dt. This is the one-dimensional solution starting from a delta function initial condition at x equal to 0. We did many improvements on this calculation. We said, let us imagine that we don't start at x, but start at some location point x0. Then how do things change? And then we found that again, things were looking very simple, that rho of x comma t was just 1 over 4 pi dt to the power 1/2. All these results are for one dimension. And in higher dimensions, it just becomes 3 by 2 in 3 dimensions or 2 by 2 in 2 dimensions. So this factor here, I have exponential of minus x naught squared divided by 4 dt. So this is a case where we don't start at the origin 0, but we start at some point here, which I might call x naught. Then we said, okay, let us suppose that not only is it diffusing, but there is some mean drift which might tend to push it in one direction. So then we said that the equation appropriate to that was delta rho by delta t equal to minus c dot delta by delta x of rho, again in one dimension, plus b delta squared by delta x squared times rho, where rho is a function of x and t. So this is a drift part. So here I have some systematic current Js, which is rho times density times the velocity c. In general, these are vectors, but in one dimension, I can just take it to be along a particular direction. Ignore that vectorial aspect of it. There's also a diffusive current, Jd. We wrote down the form of this. This is minus d times grad of rho, which is just minus d delta by delta x of rho. And we'll come back and we'll use these results a little later for other purposes. So if I have a combination of some current which says things are moving uniformly with velocity c and with density rho, and I have a diffusive current which says that if there are inhomogeneities in rho, they tend to get smoothed out by the diffusion term, then just writing the continuity equation delta rho by delta t is minus del dot j gives me these terms that I wrote out on this side. Okay. So this is how I go from here to from the currents through the continuity equation to an equation that finally has this particular form. And once I do that, I can again go and write the solution for that particular problem. So this is if I start at 0, but I'm moving with some systematic drift velocity c, this becomes exponential of minus x minus ct squared divided by 4 dt divided by square root of 4 pi d times t. Okay? So this is how we systematically generalize the problem that we started out with, starting with a simple diffusion equation here, and then moving to what I call a drift diffusion equation. And this is just the one-dimensional version of that, but you can see that I can write down, the moment I write down a general form for the systematic current and the diffusive current, I can generalize this answer to 3 dimensions, to 2 dimensions or 3 dimensions. Okay? So this is how one works with this problem and tries to get a better picture of what might be happening. The other thing that we did was, say, instead of starting with some delta function initial condition. Suppose rho of x comma t equal to 0, we initially took it to be some delta of x, which is saying that it is 0 everywhere x except at x equal to 0. But in general, we could have some more complicated expression for this, some f of x, or in general some rho of x. How would we solve that particular problem? So then we are saying that we have some initial density which might look like this, for example, and we want to ask how does this behave as a function of time? That's another question that we could ask. And then we said that the way this enters the form of the diffusion equation is if you go to K space or Fourier space, remember we have to solve the problem rho k comma t is rho k comma 0 exponential of minus d k squared times t. So this is where the delta function initial condition comes in, and this is also where any more general initial condition actually comes in. So then we said this is a product of some function of k times another function of k. So then we worked out what happened in that particular case, and we said that whenever I have a function, let us say capital F of x, which is just a convolution integral dx prime small f of x prime g of x minus x prime, then in Fourier spaces became f hat of k times 2 pi f hat small of k g hat small of k. So this is the same sort of structure that I would have here, that this is some function of k, some other function of k. So then the answer to this question must also look like this answer over here. And so the actual answer is that the density at point x at some later time t is obtained by taking an integral minus infinity to infinity dx prime rho of x prime at t equal to 0 exponential of minus x prime squared by 4 dt divided by square root of 4 pi times d times t. So this is where the x minus x prime comes in, x minus x prime squared, and this is where the initial x prime term comes in. So this is just translating from one to the other, the sort of results that we had to a more general result. Okay, and you can check that this works if you put in the form of rho of x prime. If you put in the delta function, you will see that it gives you the same answer that we had started with earlier. Okay, put in a delta function here that automatically sets x equal to x prime and gets rid of all of this. Okay, all right, very good. So now that we have done all of this, remember that we had some estimates for what diffusion constants ought to look like, and here are the diffusion constant for some, say, some small metabolite. This might be something like 500 microns squared per second, and for an average protein I would have something like 5 microns squared per second. So these are rough numbers to remember. So the small metabolite here might be something like methanol with a molecular weight of something like 30 Dalton, and this might be for the average protein, we say the molecular weight was something like 30,000. So now we want at some point in this lecture to ask what is it the diffusion constant depends upon. Metabolite is some chemical that participates in a metabolic reaction. So here it's some small molecule, in this case methanol, and we can do an experiment that says that if you look at it small enough, it's about 500 microns squared per second, whereas for a typical protein that is much larger, you have a much smaller diffusion constant. So this is saying that if you plotted it like this, then the diffusion constant versus the molecular weight is something that looks roughly like this. It goes down. The larger the molecular weight, the smaller the diffusion constant. The question is, what is this behavior exactly? Does the diffusion constant behave as 1 over the molecular weight Does it behave as 1 over the molecular weight to some power here, alpha or something like that? How do we understand that and how do we describe it? What we would ideally like to do would be to calculate a number like this based on using basic physical principles. And that is something that is important. But we won't do that right now. What we'll do is go back to the situation where we're looking at steady state. And in steady state, remember that I have delta rho by delta t. This is 0, which implies that the terms on the right hand side, just the ordinary diffusion equation, d times del squared rho equal to 0. The situation that I want to model is a situation where I have a cell here. I have a whole bunch of receptors on the cell. The typical size of the receptor is something like, let us say it's a small disk of size of radius s equal to, of radius s, which is approximately, let us say 10 angstroms. Let us say the cell itself has a radius a, which is, let's say much larger than that, maybe it's about 1 micron or larger. So the A might be 1 micrometer. And we want to ask, what is the efficiency of the cell in being able to capture a ligand that comes to it from outside? So we have some density field rho as a function of position in space r at time t, and this is the concentration of ligand which can interact with a receptor. Receptors are ligand specific, that means only certain types of molecules can come and attach to them. So we want to essentially ask the question of how many receptors must you have that are sensitive to a particular type of ligand for you to be reasonably sure that messages that are transmitted by the ligand or any signals that are transmitted by the ligand are received at the cell surface. Okay. So then we said we must solve now this particular equation here, d del squared rho equal to 0. And the way we did that was say that, look, at infinity, which is very far away, I'm going to imagine that I impose a constant, let me call it rho infinity density. At the surface of the cell, let me impose the fact that the density at r equal to a must be 0. That says that the surface absorbs anything that is incident upon it. So I have a perfectly absorbing sphere like this, coated by some ligand. The simplest problem is where I forget about the ligands and I just say there is a sphere here. And anything that lands up on the surface of the sphere is immediately absorbed. Everything at infinity maintained at a constant density. So now we have to ask what is the solution of this equation that satisfies this particular condition. So now we went from Cartesian coordinates to spherical polar coordinates because we wanted to take advantage of the fact that this has a particular symmetry, a spherical symmetry. So when I do that, the del squared operator operating on a function that is only a function of the radial distance becomes simpler. This becomes 1 over r squared delta by delta r of r squared delta rho by delta r. This is what this whole delta squared by delta x squared plus delta squared by delta y squared plus delta squared by delta z squared becomes over here. There is no term proportional to the angle theta, there is no term proportional to the angle phi, because we have assumed that everything is a function only of the radial coordinate r. So that's now what we have to solve. And then, sort of putting that back in, what we need to solve is d over r squared delta by delta r squared delta rho by delta r equal to 0, subject to the conditions on the density that it must vanish here and must be a constant at infinity. Okay. So the last time we wrote down a solution for that equation. First of all, we can get rid of the d by dr squared because it is 0. We multiply by r squared by d. Then this becomes delta by delta r of this object equal to 0, which means that this object is a constant on the right hand side, is independent of r. Then we tried to solve that, then we integrated once more because there was another delta by delta r there. And the final equation, the answer that we got finally was rho of r is rho at infinity times 1 minus a divided by r. Is that correct? So we had the condition that r should be always greater than or equal to a. So r equal to infinity, this rho of r was rho naught. R equal to a, this became 1 and 1 minus 1 was 0. And anywhere less than that, we went to 0. So the
logarithmic probability density is still valid for this rho?
Yeah, it is. It's still a probability density. It's still a density that we, where there's a probability density. No, right now it's only a density of particles because we have a condition that the density can be 0, that there is a net current. So we imagine there's a steady current of probability that particles are being input at the boundary and being eaten up here. So because of that, the direct analogy with the probability fails. This, you should just think about this as a diffusion equation with certain boundary conditions on the number. And then this is the solution that we come up with. Okay? From here, so now this is how, suppose I have the sphere here, this is center of the origin, this is the origin. At the surface it is 0, far away it rises to rho infinity. What can we do with this? First of all, let us calculate the current J, which is minus d times grad of rho. Okay. Rho now depends only upon the radial coordinate. So this thing is a vector only in the radial direction. That is, everywhere it points in the direction of the radial vector here. It points in that direction here, it points in this direction here, in this direction here, etc. So then we can write this as minus d times the radial vector r hat delta by delta r of everything here, which is rho infinity times 1 minus a divided by r. Okay? The rho infinity term goes away because it doesn't depend upon this. The only term will then be minus, the minus then go away. You get a d r hat times d times delta by delta r of a divided by r. Is that correct? Because delta by delta r can act upon, I should also put rho infinity here. I can pull out the rho infinity and then this delta by delta r operates on these two terms here. Okay? So then this becomes minus r hat d rho infinity a divided by r squared. Okay, is that correct? So I have a minus sign here. I have all my factors. The direction is r hat, diffusion constant is here, rho infinity is here, and I take a derivative of this, I put the minus sign and I get a over r squared. All right. So now this is the current that points inwards. Remember that r hat, if I have a sphere here, r hat points outward from little pieces of area there. But because this is a minus sign, this is pointing inward in this direction by an amount proportional to r squared. I can do one more thing. That is, instead of take the total current, this is the current density. The current density is J, current per unit area per unit time. But let me now integrate over the whole surface. Then what I will get is a total current. Which is the number incident per unit time. Not the number incident per unit area per unit time, but the total number incident anywhere on the sphere per unit time. To do this, I must first multiply by a little infinitesimal surface element, so that will be ds times r hat, multiply that by this j. So I should do j dot this element, and then I must integrate this over the full surface. Okay. Both of these point in the r hat direction. The minus sign will stay there. Integrating over the full surface really means integrating over the full angles that I am allowed to do. Okay, which is a factor of 4 pi. So then what I get is I equal to factor of 4 pi that comes from integrating over the full surface of the sphere, a factor of d that comes from here, a factor of rho infinity that comes from here, a factor of a that comes from here, and over here I should have an here I have an r squared term because I'm integrating over the sphere. Okay, so this element here is 4 pi r squared times that the 4 pi is the thing, the r squared dr is what I introduce at that point, because the amount of surface of the sphere increases as I go further out. Okay, so the total current incident into this is just 4 pi times d times rho infinity times a. Okay. Let me be a little clearer about that and what I did. Rather than say the total amount of current incident upon the sphere, I say let me draw a circle about the sphere. That circle has surface area 4 pi r squared. So the total amount that I get crossing any of these surfaces 4 pi r squared times this current. Okay. So the r squared and r squared will cancel. The 4 pi is what I will actually pull out and all these remaining factors. So this is the amount that is incident on the surface of radius a where particles have diffusion constant d, and rho infinity is the density at infinity. Okay. Note some very specific things. First of all, this depends upon not the surface area of the sphere, which should be a squared, but upon the radius of the sphere. And you can see that just purely from dimensional analysis. The diffusion constant here has a unit of L squared divided by the time. Rho has number of particles per unit volume, which is 1 over L cubed, and A has a dimension of length. So if I put all this together, I find that all factors of length cancel out. This just becomes 1 over time, which is exactly what this total current is. It's a number of particles, which is a dimensionless quantity, per unit time, which is coming in here. So therefore, I need this factor of A. I cannot reason this in any other way. So what I might have said is, suppose I am telling you that the sphere has radius A, that the diffusion constant is d, and rho infinity. All of these are important. What dimensionally consistent object can you make putting these three things together? The answer is the only way you can make a current is having these factors in this particular form. So that fixes everything except for the factor of 4 pi. Okay. Maybe I've been a little careless here. What I meant here to say was that I need j dot ds over the surface, but ds is r squared d omega with r hat sitting there. The r squared and this r squared will cancel. The d omega integral will give me 4 pi, and the r hat will do dot product with that r hat. So just a little inconsistency in my notation. I'm just setting that correct now. Okay. We can now say that, look, this answer is interesting. It seems to depend in particular upon one dimensional length scale. How would this answer change if, for example, I had not a sphere but a disk? Suppose I had a disk with infinitesimal thickness here and some size s. How would the current to that disk behave? Suppose I said I will only count those incident on one side and not the other side. On the other side, it just bounces off. So the answer is the current in that case is exactly like this, except there isn't a factor of pi. It's 4d times rho infinity times s, where s is this particular radius. So now you can also ask, what is the current to something that is a long absorbing cylinder, where this length is a and this radius is b. So you can say that, look, you can work this out. Let me just give you that answer here. It's the current here for a cylinder, this is for a disk, this is for a sphere. This is 4 pi d rho infinity times a divided by log of 2a divided by b. Okay. So again, look at the similarity of all of these results. This says that d, rho infinity and length scale must come, because that is the only way in which you get a quantity with the dimensions of 1 over time. But which length scale is actually relevant comes out of looking at these different examples. Over here, the relevant length scale is the size of the disk, the radius of the disk S, and there is no factor of 4 pi. For a long cylinder, the relative thing is the longer dimension, the long part A, but the factor of B comes in through a sensitive parameter that depends on a log. Because this is the ratio, it is dimensionless, so it's hard to guess. But now there are two length scales in the problem, so they must be removed in some way. And the way they enter is through this log of 2A divided by B. So just one brief statement about where you get these results. The way you get these results is to make a similarity between the diffusion problem which is basically del squared of rho equal to 0 in the diffusion problem in the time independent case, and the problem which looks like del squared V equal to 0, which is the Laplace equation in electrostatics. If you haven't seen this, this is not a problem. All this says is that because these equations look similar, they should have the same solutions, and you can use ideas from the electrostatic problem to determine what these coefficients, the d here, these factors 4 or 4 pi, the log, etc., come from doing a different calculation. And they turn out to be related to the capacitance, to something called the capacitance in the electrostatic problem, which we don't deal with. So it's just that people now know how to compute all of these by appealing to a different problem altogether. The only thing is that the equations look somewhat similar, but they are for different quantities. One is an equation for a voltage, one is an equation for a density.
B was the radius or diameter?
So B is the radius in this case. Okay, so where is this useful and how can we begin to use it? We can say, go back to our old problem, which is the problem of the sphere with certain numbers of these receptors. Let us imagine that there is these receptors here. Each receptor has radius S. S is approximately 10 angstroms, which is the same as 1 nanometer. And these receptors are stuck to the surface of a cell, which is about 5 microns in radius. So this is 5 micron radius cell, and on the surface of the cell are a bunch of these receptors, which I can assume to be disc-like. They're like these little surfaces that attach to the surface of the cell and only present one side towards the outside. Okay? So now we want to ask, what is the efficiency with which these receptors take in ligands? Since we now know what the current is just for an isolated receptor, for an isolated disk, as well as for a sphere. Okay. So suppose there are n disks. Okay. Then the current due to n disks, let us say sub n, is just n times the current due to a single disk, which is n into 4 d rho infinity times S. As n becomes larger and larger and larger, it begins to cover up all of the surface. So at some point, this result that you write down must go to another result, which is the result for the sphere, which is 4 pi times d times rho infinity times the radius of the sphere. Okay. So let us try and write an approximate form for the current with some number of receptors. Okay. So that form that we will write down is I is I naught times some function of these two scales, S and A, which I will write in the form n times S divided by A. And I will ask, what is a reasonable form that ns by A, that this function should take in order to give me the right answer in these two limits? So first of all, let me write I naught is the result for the sphere, which is 4 pi times d times rho infinity times a.
So are we taking this like as ns by a?
I will just tell you why. What I have done here essentially is pull out the factor of a and written an additional function here that depends upon both s and a. Why it should depend upon this factor is something that we will see just now. First of all, let us assume n is very large. In that limit, we know that this function here must go to 1 because the answer is just the answer for the sphere. Okay? So f of n times s by a should go to 1. Let me call this f of x. Fx goes off to becoming very large. Similarly, f of n s divided by a should go to the following quantity. So let me call this x, should go to pi divided by x in the limit that x is very small. Why is that? So let's just put those factors back in. So in the limit that x is very small, this becomes 4 pi times d rho infinity times a into, when this is very small, this becomes pi divided by x by pi, sorry, it's x by pi, I think. Yeah, x by pi, sorry. My apologies. Into 1 by pi, and x is n times s divided by a. Okay? Now I can get rid of factors, get rid of the 4 pi, get rid of the factor of a, and what I have is 4 d rho infinity times n times s, which is the same result as I wrote down here. So this is an argument that says I can always write down this particular quantity in this form here, with f of n by s being a relatively simple function. It's proportional to x here with the slope 1 over pi, and it goes to being 1 for large arguments. So if this is the plot of f of x as a function of x. Is that logic clear for how I did that? I just said this must be the function. If I choose it to go to this limit and this limit, then I get the sensible answer. I get the right answer in both those limits. And this function is a simple function that just does this over here. So suppose I want to estimate the crossover point here, roughly speaking, where it's fine to estimate it by the asymptotic value as opposed to this smaller value here. At what point does it become roughly independent of n? So the guess that one can make, which we can substantiate later, is that that happens when this argument is roughly of order 1, if ns by a is of order 1. And in fact, let me just think about that. In fact, we can do just a little better than just that. We can say it's of order when this quantity becomes of order 1. Because this is 1 here. And we'll estimate that when this particular limiting value of ns by a is of order 1. Okay? So that is x divided by pi. Let's say set that equal to 1, which means that ns by a equal to pi, or ns by pi a equal to 1. Okay? So let us now estimate the area of the cell surface. So this specifies what is the n at which these answers should roughly coincide, and the answer should then be independent of n. So let us suppose area of the cell covered by receptors. Let us now try to estimate that using this n. So that is n times pi times s squared, which is the area of a receptor on its own, divided by 4 pi a squared. Is that correct? This is the area of the cell surface covered by n such receptors. We are now going to take that n from this estimate that we made here. And now we will put it back into this. Okay? So this is let me substitute for n, should be pi a divided by s. So n is pi a divided by s. So pi a divided by s, a factor of 1 over 4 from here, times s by a, the whole squared, correct? Which then will become pi times pi by 4 into s divided by a. I got it from here, that's from the n. This contributes a factor of pi, which I will put inside. Because we said that we drew the function f of x as a function of x, and we said we started off as x divided by pi, but at large x this must become 1. Okay? So this just says at very small pi of x it starts off as pi, but we don't know what it's actually doing in between. For that we have to do the full calculation. Instead of that, let us say that the point at which x over pi becomes of order 1 is the point where these two limits will agree. This is one limit that says it has to be like this, this is one limit that says it has to be like this. So in a sense it's an estimate for the crossing point of these two limiting curves. So once we do that, we say that it happens when x over pi is of order 1, is approximately equal to 1, which is the result that I have done here. After that I keep calculating until I get this particular result. Okay? So now let us estimate this. This is pi divided by 4. Now s we wrote as 10 angstroms, s equal to 10 angstroms, which is 10 to the power 9 meters, minus 9 meters. And a was about 5 microns, so that is 5 into 10 to the power minus 6 meters. So I can write this as pi by 4, pi by 20, into 10 to the power minus 9 plus 6, which is 10 to the power minus 3. Okay? Pi by 20, we can actually calculate that, and I will leave it for you to do. I will just write down the answer. This is approximately, let us say, 10 to the power minus 4. Because the pi by 20 will come to roughly that factor. This is a very interesting answer because it says that it's enough if you cover 0.01% of the cell surface with receptor for it to become practically as efficient as if you had covered the whole cell surface with receptor. So this is one reason that explains several observations. First of all, there's a very large diversity in the number of receptors. Because receptors are targeted to specific ligands, you have to have a lot of variety of receptors on the surface to be able to absorb different types of ligands. You would like to receive these signals with reasonable specificity and accuracy. So one way to be completely accurate is to cover the entire cell surface with one particular receptor or ligand. Then you will guarantee that that ligand will always be picked up. But now what you're discovering is that only 0.01% of the surface has to be covered with a receptor for a particular ligand for it to be almost as efficient as covering the whole surface. Therefore, you can have 10,000 different types of receptors on the cell surface from this estimate here, all of which are sensitive to particular ligands, but all of which function as efficiently as if the whole surface was specifically sensitive to that particular ligand. So this is a very classic calculation, and this is by Berg and Purcell. The reference is Biophysical Journal, in 1977, and I'll circulate this so that you can have a look at the arguments that give rise to this. Okay. So among the sort of experiments that the theoretical modeling that you can do in biophysics, this is very useful because it tells you something that you would not have guessed. It's very hard to guess that I can cover the cell surface with just 0.01% of receptor and have it being as efficient as covering the whole cell surface with receptor. And the physics behind this is, roughly speaking, that a ligand spends, if a ligand is not absorbed, it spends a lot of time in the vicinity of the surface. So thereby enhancing its chances of being absorbed at one or the other of the receptor surfaces. So it's not as though it's just a one-shot thing of coming here and then going back to infinity. Once it reaches near the surface, it spends time in the vicinity of that surface, repeatedly sampling the surface. So even if you have a relatively small number of these attractive or patches, sooner or later it will try and find them because it spends time in there. Okay, so with that, we finish this particular discussion on chemoreceptors. And let us just do another calculation now, which is something called the Einstein relation. Remember that what we wanted to do was we said that, look, if we plotted D as a function of the mass, it sort of looked as though it was coming down, but the relationship wasn't clear, at least from those two pieces of data. And presumably diffusion constants depend upon other things. For example, you might expect them to depend upon the temperature, certainly would be an important thing. And you might expect them to depend upon some properties of the fluid in which this object is diffusing, whatever you're looking at. The more slower motion in that fluid is, the more slower diffusion is. You might expect that that's a rational consequence of the arguments that we have been making. So the Einstein relation is one way of putting some bones on this argument and trying to understand what is it that a diffusion constant depends upon. So first of all, let's just write it down in one dimension, and let us write down our expression for the total current, which is a systematic current and a diffusive current. And this part is, of course, some velocity times the density, and this part is minus d of the gradient of the density. So that is d rho by dx. Okay. First of all, let us ask, what is making it move with some velocity c? Let's imagine that we have put it in some potential here. So you have a bunch of particles density here, and being pushed down by some force that is acting on the downward direction, and this force comes from a potential. So you know the relationship between a force and a potential. A force is just the derivative of a potential, dVx by dx, or dux by dx with a minus sign. Okay? So if the potential is in this direction like this, large and small, this will tend to move down here. To reach the minimum of the potential. Given this potential, one can now ask, what is the density of particles rho of x within that potential? So now I'm going to bring in one result that we have not dealt with yet, but is important. We will derive this a little later, but I will just write down the result now. Rho of x is just the average density, let me call it rho naught, exponential of minus beta times u of x. So rho naught is the average density. Beta is 1 over the temperature times the Boltzmann constant. Remember that we dealt with the Boltzmann constant earlier. So this is an energy. The u of x is the potential that the particle is seeing itself in. So what this is saying is, suppose there is some complicated potential here. The density tends to be larger at points where the potential is lower, so it sort of maybe looks a little bit like this. The lower the potential, the higher the density in that point relative to its average value. If u of x was 0, then I would just have a constant density throughout. There is no potential, and therefore the density must be a constant. If there is a potential, then particles tend to be a little more in the wells of the potential and less on the peaks of the potential. The extent to which they tend to be closer to the wells of the potential is captured by this factor, which also includes the temperature. We also know this, that something like this is sensible because at very high temperatures, particles don't care about the potential. They will just be sort of uniform. At very high temperatures, the 1 over kBT factor goes to 0 because T is very large. So exponential minus 0 goes to 1, and rho of x must be rho naught. Okay? So that's a sort of physical justification. I have not shown you a formula like this. This is, you can call it a Boltzmann relation, but we will come back and derive this in some detail because we will need this in almost everything that we will do in the future. The next thing that we need to do is, we're going to look at steady state. And steady state is where the total current, J total, which is J systematic plus J diffusive, must be 0. And so the way to think about this is that suppose I have a force or a potential that is pushing particles downward. At some point the density here will be larger than the density above. But particles, because of diffusion, always tend to move from large density to low density. So this will tend to smooth it out. So what you must have is some compromise between piling things up due to the force and things trying to relax because of the density. They don't like density to be accumulated in one particular point. Okay. Alright, so now if we say this, then we can take this term here to this side and balance these two terms. So d times d rho by dx must equal c times rho. Rho is rho infinity e to the power minus beta times u of x, the potential. So d rho by dx must be rho infinity e to the power minus beta u of x times the factor of minus beta from here times du by dx. Okay, I'm just taking the derivative of this particular term here. Now we need to think about things on the right hand side. In particular, we need to ask, what is c? What is this velocity? So here is my diffusing particle. It is experiencing a force F, which is minus du by dx. Because it's experiencing a force, you might have thought it would try to accelerate, but it's always surrounded by liquid, by some fluid here. That will slow it down and tend to make it move with a constant velocity and not accelerate. So the way to estimate that is, say that the velocity is, let me just write it in words first. Velocity is a mobility times a force, or a force is a friction coefficient times the velocity. Which I will call zeta. So the mobility and the friction coefficient are like inverses of each other. Okay? So now we simplified with this the left hand side. Now we have to work with the right hand side. So let us write C of rho. So the right hand side is C, which is 1 over the friction coefficient, okay, which is mobility times force, which is 1 over friction coefficient times the force. So this is 1 over the friction coefficient times minus dux by dx, which is the force, times the density, which is rho infinity, e to the power minus beta times u of x. I'm just writing out these terms, making some specific approximations for the terms that enter here. And now we can put everything together, because this term here must equal this term to the left hand side. Okay? So on the left hand side I have d times rho infinity e to the power minus beta times u of x minus beta times du by dx equal to this term on the right hand side. But now I can get rid of this factor here, I can get rid of this factor here, I can get rid of this rho infinity here, I can get rid of the rho infinity here, I can get rid of the du by dx here, I can get the du by dx here. The signs of course go away. So what I have is beta times d equal to 1 over the friction coefficient, or d is kBt divided by the friction coefficient. This is so important that it has its own name. This is called the Einstein relation. So this says you can estimate the diffusion constant with the following argument. The diffusion constant is proportional to the temperature, linearly proportional to the temperature. The larger you make the temperature, the larger the diffusion constant. But it's also inversely proportional to the friction coefficient. That is to say, if I take a particle, I try to move it with some velocity v through the fluid, then the fluid will resist that and exert some force on me in the backward direction. And that force is a friction coefficient times the velocity. And that is what enters here. So we can go a little further by using a result which we will again maybe derive at some point, but maybe we won't, we'll just state it like that. And that is the result due to Stokes. And Stokes was considering a fluid with a particle in it, and the particle moving in it. And then he said that the force F acting, if I move this particle with some velocity v, the force acting to keep that particle not moving is 6 into pi into some property of the liquid called the viscosity times the radius of the liquid times the velocity. The radius of the object that you're trying to move times the velocity. And this is the radius of the sphere. Okay? So just going back to the definition of the coefficient here, the friction coefficient or the drag coefficient here, force is friction times velocity. Therefore, this object here must be the friction coefficient theta. So now we can put all of these results back in the following form. I'll just write the final answer, then I'll come back and answer that. So now the diffusion constant is kBt divided by 6 pi times beta times the size of the object. And this is called the Stokes-Einstein relation. And it's very important, not just in the approximation that we will make in a biophysical context, but in a whole lot of physics that has to do with software. Okay, what is the question? Eta is something called a viscosity, and this is a property of the liquid. Eta is a viscosity, and we can estimate, we can figure out what its unit should be by looking at this. The unit is force is mass times acceleration. So this is the units of, let us say, kg on the left hand side, times acceleration is a length divided by 2 factors of time squared. On the right hand side, 6 pi has no dimension, so we don't have to bother about it. Eta is the dimension we want to find out about. I have the dimension of a, that is just a length scale. So I must put in 1 factor of a length here. And then I have a velocity, which is a length per unit time. So I must put in a length here and put in a factor of time here. Is that correct? This first term here is the force. And this I can get from F equal to ma, which is the mass times an acceleration. An acceleration is the length scale divided by 2 factors of the time. The term on the right hand side is a length scale here, which I have brought down over here. The last term is the factor of velocity, which when I bring down here becomes a length and a time on top. So now let me simplify. I can remove a length here, a time here, and 1 unit of the time here. What I will get is a kg divided by a length scale L divided by a time scale. So one way to trace this is a kg per meter second would be the unit of viscosity. Or equivalently, I would have gram per centimeter second. And this unit is called a poise. So that is something that you must get from an experiment. It's a property of the liquid, not of things inside the liquid. Okay. So for water, at say room temperature of about 27 degrees centigrade, the viscosity is approximately 10 to the power minus 2 poise. So that's a way of estimating it. But poise meaning gram per centimeter second. A is the radius. Okay. Okay, so now we have a lot of really important results on the thing. We have the Einstein relation, we have the Stokes-Einstein relation. Now we can try to estimate something. So let us assume that we're going to look at a really small object. Let A be approximately 10 angstroms. Let the temperature be about, let us say, 300 Kelvin. And we now want to estimate, that's all, and you know what the value of eta is. We now want to estimate what D is. Now you have to be careful here because there are many units. There's a unit of temperature which you have to convert to the right unit. This is the CGS unit because it's gram per centimeter second. So you must compare when you this is angstrom, which is 10 to the power, so 10 angstroms is 10 power minus 9 meters. So you must be careful about how you convert all of this. So I will leave this for you to do as an exercise and compute from here what the diffusion constant is. Similarly, compute from here what the diffusion constant is if you have A equal to not just 10 power minus 2 poise, but A equal to 1 micron. Instead of A equal to 10 angstrom, what happens when A equal to 1 micron, keeping everything else the same. Okay? So there are some things that this relationship tells you. This is a property only of the liquid. This is the property of the temperature in which the system is. The only place that the actual object that is moving enters is through this quantity A. So this is a very unusual thing. It says that the diffusion constant does not depend upon the mass of the object that is moving. It does not depend upon the amount of surface area that is moving. It only depends upon one quantity, which is the characteristic dimension, whether you call it A or 2A, of the object that is there. And remember that earlier we said that we wrote down a diffusion constant as a function, and we sort of plotted some points here. We had some numbers for it. What would be if there was a small metabolite, if there was a large protein, mid-sized protein or something. And we said this goes roughly down with molecular weight. And the question was, how did it go down? What is the sort of relationship between this? If you assume that this is roughly at the same density, then the weight is just a density times a dimension cubed. Okay? So, let us say a mass is a density into a volume. Let me assume that the volume is, everything is roughly spherical. So the volume factor is always something like A cubed. So therefore, and if I assume that the density is roughly the constant for whether it's something that's small or big, then the mass is then proportional to A cubed, which means that A is proportional to the mass to the power 1/3. So now I can put that back in here and say, how does the diffusion constant depend upon the mass or the molecular weight of this whatever I'm studying? The answer is it depends fairly weakly. It only depends upon the 1/3 power of that, which is why it was hard to sort of infer just from this what the relationship was. But this is the prediction that you might have for how as a function of size, because it just follows from the fact the diffusion constant only determines, is only a function of the linear size, of the characteristic linear size of the system, not of A cubed, which would be like the volume, and therefore would go into determining the mass. Okay? So what are we going to do from now on? These are all very important results, and I will try and give you some homework that emphasizes the calculation of all of these things. I want you to just try these examples as practice so that you get a good idea of what a diffusion constant is, what it depends upon. These are very important and fundamental results at every level of biophysical modeling. So it's important that you understand this well enough and have no difficulty interpreting it. What we will do the next time is begin to think about this question of, first of all, where did we get this relationship rho equal to rho infinity e to the power minus beta times u of x? Where did this come from? So to do this, we'll have to learn a little bit of statistical mechanics, and before that we have to learn a little bit of thermodynamics, because there we will get into the idea of what is entropy, what is the free energy, because these are words that you will see a lot in any sort of biophysical modeling. So we need to understand what is entropy, is free energy, the Gibbs free energy, Legendre free energy, how to calculate the simple things in statistical physics, and finally how to understand and appreciate an equation of this particular form, where it comes from and how to understand it. Okay, that's one particular point. The second thing that we will need to do, we'll do a little later, is to try and understand a quantity like this. What does it mean? Where does it come from? And what is the implications of a viscosity? If I give you a fluid with a certain viscosity, how do I predict the properties of that fluid? It turns out that given the viscosity of a fluid and the boundary conditions that I've imposed on the fluid, that's enough for me to be able to calculate properties of that fluid. So what are the equations that govern the behavior of fluids is something that we will write down in later classes. So these are the two directions which we will take right now. But immediately after this class, we will concentrate on this particular question of what determines this sort of behavior. And to do that, we have to learn a bit of thermodynamics and a bit of statistical physics. Is that clear? Any questions? Okay then.